So thank you for introducing me. My name is Justina Jaseliūnaitė. I work in Lithuanian Energy Institute Laboratory of Nuclear Installation Safety. I am, as I said, junior researcher, and also I'm a third-year PhD student. So, it's pretty frustrating when our gadgets overheat. We all been there. You are in the middle of an important call or a gaming session and suddenly your phone feels like it's on fire. Or maybe you're working on your laptop trying to meet a deadline and it just shuts down because it's too hot. It's not just annoying, it's stressful. Imagine being a student whose computer crashes during an online exam, or a professional who loses its unsaved work. It's a nightmare. And the root of this issue often lies in poor thermal management. Electronics generate a lot of heat, and if that heat isn't managed properly, it can lead to all kinds of problems. Components can degrade faster. In worst case scenarios, the device can fail altogether. But there is a potential solution on the horizon. It's micropin arrays. These tiny structures can be integrated into our electronic devices so that the heat transfer can be improved. By increasing surface area and enhancing flow around components, the heat can be managed properly so the temperature of the device is kept in check even under heavy use. But before that, we need more research. And using CFD is a good choice, because by using CFD, scientists can make different configurations, check whether one flow conditions is better than others, and so that the heat will be managed properly and we will use our gadgets more freely and often. As I have told you about the problem, I will now present the research. So here you can see a picture of a real microchip, which has designed and investigated by Renfa. It is pretty small. It's just 1 centimeter on 1 centimeter, so it could fit in your finger pad. And here is a numerical representation, a channel full of cylindrical obstacles. These obstacles are called pinpins. The channel consists of 50 obstacles in both directions, so in total there is 2,500 obstacles. I haven't used the whole channel for simulations. I took only a part of it, which you can see here. The height of the channel is 200 micrometers. The pitch between pins is 200 micrometers, and the pin diameter is 100 diameter. For research, I have modified the original geometry a bit. I changed the pin shapes to cone and hourglass. The cone has a degree of angle of 4 degrees, while hourglass has a twice larger. Besides that, all the geometries has the same cross-section and flow volume. Now shortly about initial conditions. The fluid was had the properties of water of 22 degrees. Investigated Reynolds range was from 178 to 735, and I used detached eddy simulation with K-omega SST turbulence model. Moving next to boundary conditions, for inlet and outlet I used mapped boundary conditions. Left and right walls were set as cyclic, and walls as usual had no slip conditions. Also, both end walls were heated with 72 watts per square meter heat flux. As the main investigation of this presentation is related to omega criteria, I want to introduce what it is, what meaning it has. So simply saying, it shows when vorticity overtakes the formation. Also wanted to mention that this is a third generation vortical structure identification method. Some of you may know second generation methods like Q or lambda. So vorticity is described as a curl of velocity and deformation as a rate of strain tensor. These two terms are not independent. The shear strain rate decreases as the vorticity increases. To be more specific, omega has the following expression, where Frobenius norms of both antisymmetric spin tensor of vorticity and symmetric rate of strain tensor is taken into account. It is this expression that makes it possible to scale values from 1 to 0, thus avoiding threshold value use and estimation. I hope you all get an idea of what omega criteria is. Now that you're aware of the geometry and modeling conditions, let's move on to the grid independence. Here you can see results of grid independence index. I've checked 3 meshes with cells numbers you can see in the upper part. Out of all these numbers, the most important are extrapolated relative errors for fine and coarse meshes, as well as the numerical uncertainties for fine and coarse meshes. We can see that the difference errors for coarse mesh is almost 2%. While uncertainties is 2.5%, while both units for fine mesh does not reach 1%. Therefore, for further investigation, cells were selected between the finest and the average, depending on the geometry used. Further use of the numerical model requires not only grid independence, but also validation with real experimental data. Here you can see the graph of pressure drop versus Reynolds number. At laminar regime, there is little to no difference between the experiment and modeling. But as Reynolds gets higher, the difference can be seen. But this can be explained by using small domain instead of the whole channel. In my simulations, there is no influence credited for inlet and outlet. But nonetheless, the mean relative error is 10%, which is considered adequate and good. I'd like now move to the results. The graph shows pressure drop versus Reynolds number for all configurations. You can see that there is no big difference between cases. Hourglass-shaped pin-fin array has a slightly higher pressure drop at non-steady regime, while in laminar regime it seems to have the lowest pressure drop. Now I would like you to present how flow structures looks like in all configurations. Here you will see a video of velocity vectors scaled by velocity magnitude, and there is clear distinction between cylindrical pin-fin array and 2 others. The conicity disturbs flow more and directs it according to the geometrical features. We can see that in cylindrical pin-fin array, the flow is distributed evenly over the entire height. While in cone and cone pin-fin array, the flow is directed to the upper part where the cross-section is larger. And in the hourglass-shaped pin-fin array, flow is also directed, but now to the middle part, also where the cross-section is largest. When the Reynolds number is lowest, there is clear distinction between flow in different geometrical configurations. To confirm this statement, velocity profiles from end walls to end walls is shown in the graph. We can see that cylindrical pin-fin has the smooth profile, hourglass is curved more in the middle, and cone has a strong curve in the upper part, the flow cross-section increases. Let's look what happens in the flow. I added sketch topology to the arrays. I also added stagnant vortices. And what I wanted to point out is jet-like flows in cone and hourglass pinfin arrays. These geometries causes opposing jet-like flows along the pin surface, which are directed from walls towards the middle in the hourglass case and towards one end wall in cone case. The jet-like flows collide, thus creating more vortice dissipation and stretching and all kind of interaction. Moving on to the investigation of omega criteria. By using omega, I received data of vertical structures volumes, the graph on the left, and the surface area of vertical structures, the graph on the right. As you may see, there is sharp increase in both graphs. This increase shows that the flow becomes unstable. This instability causes vertical structures volume to increase by 36 to 40% and surface area about 15 to 20%. I should also note that vertical structures volume after transition continues to decrease, while surface area shows different trend. This can be explained that vertical structures become smaller as Reynolds increases and thus surface area increases. Let's see how these structures looks like at the highest and lowest investigated Reynolds number. At lowest Reynolds number, structures are stable, while at highest, they stretch, collide, dissipates. Even from this video, we can see that there was more action, collisions, and dissipation in cone and hourglass shaped pinfin arrays than in cylindrical case. That's why in a volume graph at highest Reynolds, you can see the large enough difference between cases, where cylindrical pinfin array has largest volume occupied by vertical structures. So from this, we can say that so there is some slight discontinuity, but cylindrical case has the largest vortices, while cone pinfin array has the smallest. As I talked about vertical structure identification by omega criteria, let's take a look at its mean values in the whole domain, the graph on the left, and just in vertical structures, the graph on the right. There is no doubt that again we notice the increase in values after transition. This increase in mean values in the whole domain is just about from 2 to 3%, but the increase of omega values in vertical structures can reach up to 10%. Therefore, with all these results in mind, we could use omega as a parameter which recognizes transition from laminar regime to unstable. So, in conclusion, non-uniform cross-section results in more disturbed and dispersed flow structures. Vertical structures volume after transition increases up to 40%. Vertical structure area after flow transitions increases up to 20%. And omega can be a new identifier of flow transition. Thank you.
Okay, thank you very much. We take questions.
The pictures you show in the background are interesting. Some of them are made by AI, right?
The first ones, yes. Yes.
Yeah, and you made it by GPT. Or...
Yes, ChatGPT.
Since I'm not so familiar with the top flow, I have a very basic question. By selecting the representative simulation geometry from the whole cooling system,
Yes.
Do you know that is there any other turbulence pattern which exists in a larger scale than the unit square shaped issues?
It is scalable. Like this, you can have, if I correctly understand, you can have big channel, but you can have small, and the turbulence is the
I
same.
mean, what if you have multiple pins in one simulation? What's from it?
Oh, the full channel?
I want to know if that makes a difference.
I modeled the full channel, like with all the obstacles, and it gives the same results. I have validated in articles, so I didn't show it here due to time. So
Any other question?
Thank
you very much. I noticed you calculated GCI rate convergence index.
yes,
To my knowledge, you have to calculate the order of your simulation to calculate this index. I wonder how you can simulation complex. To my knowledge.
other. What do you mean by other calculation?
Or can you explain how you calculate GCI?
I done several simulations with different meshes. Then I took one parameter, which was pressure, and then I calculated all by the that methodology. That's yes, yes, of course.
No question online. May I know which software have you used for simulation?
Yes, I used Boolean form. I guess how it's called. The one used for heat transfer applications in OpenForm.
It's open source code.
Yes, OpenForm.
Okay.
The same OpenForm.
Open source, yeah. Okay. And did you consider post-net approximation? Actually, I can answer this question. It's a K omega SS based DS, right?
Yeah.
So sure, they consider post-net approximation.
Yes.
Okay. Another question. No? Okay, time is up. Okay, let's use one more time.
Thank you. Thank you.